Would you believe you're looking at gold? Right now you might be thinking, come on man, that's not gold, it's Kool-Aid. And I think you're drinking it. But no, it really is gold. A suspension of gold nanoparticles, and today we're going to make some. They're too small to see individually, but we can detect them with a laser. We'll also learn why they're red and how these unseen nanoparticles can be injected into patients and zapped with a laser to cure cancer. We're going to start by taking some chloroauric acid. That's an acid that contains gold ions. That's pretty cool. Do you see the yellow color? That's due to the gold ions in the acid. And these gold ions have a positive 3 charge. You can't see this laser beam when I shine it through the solution, and that's because the ions are dissolved individually. They're atomic scale, way too small to scatter light. Watch how easy it is to convert the acid into gold nanoparticles. We first get the chloroauric acid good and hot, and then add some sodium citrate. You can see me at it right here. Did you also notice that it's changed from yellow to colorless? That's because some chemistry is happening. The +3 ions in the gold have been reduced to +1 ions. Hey, check it out, it's turning blue. This means some nanoparticles of metallic gold have formed. Let me collect a few of these for later. These gold nanoparticles are blue because they have +1 gold ions on the surface. But get this, those surface gold ions continue to react with the citrate ion. This converts them into gold metal. And with that chemical change comes a change in color to red. If I collect some now, it's probably a mixture of the two forms, the blue and the red. But as the reaction keeps going, all of it gets converted to the red form. And we've got our gold nanoparticles. Here, let me collect some of these gold nanoparticles too. Watch this. If I dilute the suspension of gold nanoparticles with some water, it really makes that red color pop. We can see evidence that there are tiny undissolved particles here by shining this laser through the mixture. Check it out. You can see the laser beam. That's because there are particles large enough for the light to bounce off of. Those are the nanoparticles. Do you remember this experiment with the chloroauric acid? In that case, we couldn't see the beams shining through the solution. That's because everything in the acid is completely dissolved and there's no solid particles anywhere for the light to bounce off of. And if you're interested, here's a comparison of the 3 different samples I collected throughout the process of making the nanoparticles. But how do they get their color? Well, imagine we have a bunch of gold atoms in a nanoparticle like you see here. When light hits the nanoparticle, it causes electrons on the surface to slosh back and forth in one giant collection called a plasmon. The plasmon wiggles back and forth over the surface at the same frequency of the light that's hitting it. The frequency of the wiggling depends on a number of things like the size of the nanoparticle, its shape, what's on the surface, and the liquid that it's in. In this case, these gold nanoparticles wiggle at the same frequency of green light. So they absorb green, but red passes right on through. And so it looks red to your eye. But scientists can change what's on the surface, and this makes the nanoparticle absorb different colors of light and appear a different color. Like at the beginning of the experiment when the gold +1 ions were on the surface, those nanoparticles appeared purple or blue. Now the wiggling electron plasmon is really big. So big that it has a hard time keeping up with the fast wiggling of the light. And it ends up giving off a lot of this light energy as heat. And this is where the cancer therapy comes in. You can inject gold nanoparticles into someone's blood. Gold is very unreactive. So the nanoparticles are much less likely to mess with your body than traditional chemotherapies. You see, the veins and arteries of cancer tumors are leaky. Well, leaky enough to allow the nanoparticles to pass out of the blood and into the tumor. On the other hand, nanoparticles don't build up in normal tissue because their veins are not leaky. So the nanoparticles concentrate in tumors, but not healthy tissue. Doctors then zap the area around the tumor with an infrared laser. The laser light's not absorbed well by the body, so it passes right through. Kind of like this. But the cancer-fighting nanoparticles are tuned to absorb infrared light. And when they do that, they heat up. And that kills the tumor. That's not too bad for a bunch of tiny particles that you can't see. See it? Oh, yeah. It's like darkening?
Yes.
A little bit? Oh, look at that. Come on, baby.
It's going to be purple later.
All right.